Okay, hello and welcome to another presentation, this time on enumeration. Now this can be a very tricky topic to teach, and it's brand new really to the GCSE specification. It wasn't really included in Edexcel's specification for A-level either, so I'm quite happy, I guess, to see it in there, but it is going to be quite tricky to teach students this. It's certainly a topic which only the very strongest students will really conquer. That said, even quite weak students can get the hang of the basics, so let's just jump into it with this problem right in front of us. Now, as I'm sure you're all aware, the bank allows you to choose your PIN for your debit card. How many possible PIN numbers are there? That's just my first question. Well, we can think about this we can think about it in a lot of ways, to be honest. Probably the easiest way to consider this, and I'm pretty sure you'll agree here, is if your PIN number goes from 0000 up to possibly 9999, well, surely then there's going to be 10,000 possibilities, because you've got every single number there represented from 0 right the way up to 9,999, and that would be 10,000 possibilities. So that one's quite a simple example to start off with, but somewhat annoyingly I'm going to show you a slightly different way of thinking about it, just because this alternative way of looking at it works for plenty of other cases as well. I'm going to talk about something which I refer to as a possibility tree. Now, I'm not going to draw out the whole tree because it's going to have 10,000 leaves on it, but I hope that you'll get the idea. Okay, so we know the answer is going to be 10,000, but let's just look at it in a slightly different way. Because your first choice, you've got 4 digits, let's just draw little boxes to represent our 4 little digits. Your first choice, you could choose any of the numbers, or symbols if you like, from 0 to 9. Now, how many possible numbers are left from 0 to 9? There are, in fact, 10. So, if I was drawing a tree to represent all possibilities, a bit like a probability tree, in fact, exactly like a probability tree diagram, there would be, starting off, 10 branches, yeah? Now, I'm just going to draw those. I'm not even going to be able to fit them all on. Let me see if I can just tidy that up. So, looking at this diagram, I've just quickly neatened it up. We're going to have 10 possibilities for our first pick. Now, of each one of these branches, and I'm not going to be able to draw it because there'd just be far too many branches, for the second choice, for your second digit, you're going to have 10 possibilities coming off of those. Now, I hope you can see where I'm going with this, because that's going to give you 10 times 10 to count all the next branches, times 10 to count the branches after that, and then times 10 to count the branches after that, which is, of course, 10 to the power of 4, which is the same answer as before. It is 10,000. Now, you're probably thinking, why am I showing you two different ways of doing that? It will become clear in a second when I approach the next few problems in exactly the same way, because I think it's a nice way of looking at it, thinking about a possibility tree. Okay, let's go back to the next question, because that first question is pretty straightforward. Okay, so our next question is, well, let's just say I like my PIN number to be a multiple of 5. How many possible PIN numbers are there now? Now, some of you might be thinking, well, this one's straightforward as well, and to be honest, I would agree. But let's just look at it in exactly the same way as we were before. Okay, so using that possibility tree, which I now want you to just think about in your head, obviously if a number's a multiple of 5, only the final digit matters. And there the final digit will have to be 0 or 5. So I've still got 10 choices for the first one, 10 for the second, 10 for the third digit, and then only 2 for the final digit, because I want it to be a 0 or a 5. That gives me an answer of 2,000. Now, some of you might well be saying, well, that's obvious, because there's going to be 2,000 multiples of 5 from 1 to 10,000. And I would absolutely agree with you there. So these first two questions are absolutely fine. Let's have a look at part C, though, where it starts to get a little bit more interesting. In part C, I'm now insisting somewhat strangely that my PIN number mustn't contain the digit 2. Maybe I'm superstitious and I find the digit 2 unlucky or something like that. How many pin numbers are possible now? And this is where I really like thinking about the possibility tree, because it makes it quite straightforward to do. So we don't want the digit 2. Well, in that case, for the first choice, I've now only got 9 digits that I can choose from, because I don't want the digit 2. And from 0 to 9, there are 9 numbers which aren't 2. The 10th number obviously is 2. You've got 0, 1, 3, 4, 5, 6, 7, 8, 9, and there are 9 digits there. So you've got 9 branches, if you like, on your possibility tree for the first one. It's going to be exactly the same for the second one, so we're going to be doing 9 times 9. And the third one, so we're going to be doing 9 times 9 times 9. And for the fourth one. And therefore, the number of pin numbers possible which don't contain the digit 2 are 6,561. I think that's right. Let me just check on my calculator. Yeah. So yeah, and we've done it. That's a nice little gentle start. Now, believe me, this kind of counting, product rule for counting, can get a little bit more difficult, and we're about to see why. Okay, here's a different example. This is about 6 children. They're going on a school trip. There's 6 seats available on the bus. In how many ways can the 6 children seat themselves on the 6 seats? So how many possible arrangements are allowed if 6 children are sitting on 6 different seats? Now, it helps to call the seats here A, B, C, D, E, F, I think, for just visualizing it in your head. Let's have a think about that. Okay, so what's different about this problem? Well, it almost helps when you're doing arrangements to think about this temporally. By that I just mean think about it as a process in time, because that's what actually happens really. Firstly, let's say they just all jumble themselves up, shuffle themselves in, just before they get on the bus, and then we get one person going on, then the second, then the third, then the fourth. Well, if we think about our possibility tree, we're going to have 6 choices for the first seat. But here's where it gets different, because we're only going to have 5 choices for the second seat, because one of the seats is already taken. And I hope you can see where I'm going with that. I won't draw the rest of the tree once again, because it gets far too big. But can you see you're going to have 6 possibilities for the first one, multiplied by 5 for the second, multiplied by 4 for the third, dot, 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 all the way down to the last one where he's just left with 1 choice to sit down, and so we only need to multiply by 1 for him. Now, for those of you who've seen this notation before, yes, that is 6 factorial. That is a way of notating 6 times 5 times 4 times 3 times 2 times 1. So, for example, 10 factorials, 10 times 9 times 8 times 7 times 6, all the way down to 1. That is just notation, and it is always the way you can work out the number of arrangements, yeah? For example, if I've got 9 books which I'm putting on a shelf, how many different ways are there of arranging those books? Well, I've got 9 choices for the first book to pick up, 8 choices for the second book to pick up, so on and so forth, so that would be 9 factorial. And that's always the way we work out problems when we've got arrangements. But notice it is slightly different from the first problem we were dealing with when we were looking at all possible cases. By the way, I should tell you the answer to that. I think it is 720. Okay, right. Let's have a look at the last type of problem, which I just want to mention because they could conceivably make it this difficult. Okay, so this last question is simply this. Let's say I have a class of 7 people and I'm selecting 2 of them to represent the school in a maths contest. How many different possible pairings are there? Now, what I'm essentially saying here is, let's say I've got 7 names of students, Alan, Brenda, Claire, Dave, Edward, Freddie, and Gerald. I think I'm up to 7, aren't I there? Yes, I'm up to 7. I'm trying to think of all the different possible teams I've got. Let's have a think about that now. Now, initially, you might think along the lines of, surely this is the same as the last problem. We've got 7 students, and so we're going to have 7 possible picks for the first team member. So 1, 2, 3, 4, 5, 6, 7. And then 6 for the next team member. So surely the answer is, I hope I've done 6 there, I think so. Surely the answer is just going to be 7 times 6. And sadly, you would be wrong. Now, why is that? Well, it's because I'm just pairing these students up. And unlike both my previous questions, here the order is unimportant. In both my previous questions, the order in which I was doing things was important. You know, for the pin number question, a pin number of 2173 is very different to a pin number of 3712. But in this question, if I have a team of, let's say, I think I called them Alan and Brenda, that's exactly the same team as Brenda and Alan. And so on my possibility tree there, if I list all 42 leaves, on one of the leaves you will have Alan and Brenda, but on another leaf you will have Brenda then Alan being selected. In other words, you've counted all the teams twice, and therefore you need to divide by 2 at the end, giving you 21. Now, for those of you who've done permutations and combinations before in A-level, and not all the exam boards do it, but some of them do, I think OCR does, you can actually do this a quick way, which is you just need to do 7 choose 2, yeah? 7 choose 2 equals 21, and that is a perfect way of doing it, because that is what the n choose r notation means. It's a number of ways of choosing 2 objects from 7 when the order is unimportant. Now, I'm just mentioning that to those people who've covered this in A-level before, just to kind of link to it. But if you haven't, don't worry. You can just think of it as I have done here as a possibility tree, but bear in mind that you may have counted some people twice. Look out for that one, because that's quite a tricky one. It gets even trickier, to be honest, if we were picking 3 people from 7, because we wouldn't be dividing by 2, we would be dividing by 6 at the end, and I'll leave you to think about why that would be the case. I'm going to leave this presentation here. Best of luck with this topic, which is no doubt a tricky topic. There's a few questions in the unit assignment on this. I hope it goes well, and if you're finding it pretty tricky, do remember to mention it in the next online